I recently went back to headquarters and our CEO came in and spoke. And the thing that he said that I thought was a very efficient way of expressing the need to get going is AI today is on an exponential curve, and you do not want to be late to an exponential curve.
Hi, I'm Stephanie Tumampos, and you're listening to Down to Earth, the show where we talk to incredible geoscientists about their science and its impacts on our planet. This season, we're exploring the many ways we can harness the power of artificial intelligence to learn more about our world. I'm also on a personal quest to discover if AI will be more of a help or more of a hindrance to our work as geoscientists. Today, we're jumping in at the beginning of this exponential curve to discuss the hardware, infrastructure, and software stacks for amazing work in GeoAI. This episode of Down to Earth is brought to you by the Geoscience and Remote Sensing Society's technical committees. As part of the world's leading professional association for the advancement of technology, the GRSS technical committees are innovation hubs, bringing together experts from around the world to forward cutting-edge geoscience research, development, and applications. To learn more and be part of the premier community driving the future of geoscience and remote sensing, visit grss-ieee.org and join a technical committee today.
After finishing graduate school, started immediately working in the defense and intelligence community, helping them make sense of data as it was collected. In those roles, I found probably about 10 years ago, right when convolutional neural networks started making big splashes in the computer vision world, getting applied to other modalities, I was given a very similar problem, just with geospatial overhead, remote sensing data, and started playing with neural networks to solve that problem. It was quite difficult at the time. It was early days. Hardware availability, particularly within government environments, was challenging. So it was hard to do, but really exciting. And so that introduced me to NVIDIA hardware, the sort of beginnings of the software that has now evolved at NVIDIA to support AI researchers.
This is Dr. May Casterline, Principal Solutions Architect at NVIDIA. With a background in infrared modeling techniques, optimization algorithms, and thermal measurements, May now brings her geoscience experience into her work as a technical face of NVIDIA. What this means is that she engages with folks from both industry and government to help them leverage NVIDIA technology along their project design and implementation journey. This is a pretty exciting role for May because it allows her to solve all kinds of different interesting and hard problems, so she's constantly learning about AI hardware and software infrastructures.
I actually started out looking up, did a lot of astronomy work in my early career, but turns out there's a lot of interesting things when you look down. So I transitioned to remote sensing and then moved down to the Washington, D.C. area and did a lot of work helping the government make sense of the Earth. And May convinced me that maybe NVIDIA would be an exciting place to work. So here I am.
And this is Dr. Brent Bartlett, Senior Solutions Architect at NVIDIA. Brent's expertise is in geospatial applications with an emphasis on remote sensing with airborne and spaceborne imagery. Over his career, Brent has worked on many projects that apply accelerated processing techniques to large-scale geospatial imagery analysis. Brent is particularly enthusiastic about the ways NVIDIA is pushing research in areas including accelerating physics and understanding complex segmentation for remote sensing. Together, Brent and May help developers, engineers, data scientists, and analysts integrate artificial intelligence and GPU-accelerated solutions into their workflows and products. I'm really excited to learn all about the advancements in AI-supportive hardware and infrastructure from these incredible experts. So, let's dive right in. So today, we're looking at the hardware and infrastructure that enables us to use AI. So let's start with hardware. What are the most important hardware components needed to support AI models and processing?
So it's a loaded question because it's never just hardware. And I think that's pretty evident in how NVIDIA is going to market these days. Clearly, we started as a hardware company with graphics cards. Today, though, we make a lot of things. We make GPUs that are consumable all over the place. We have a whole networking stack. We even make CPUs at this point. We make small modules that are effectively small miniaturized computers that have GPUs and CPUs and all of the components you need to run a full OS and processing. So we make a whole lot of hardware. In concert, we work with a lot of partners to put those pieces together. So you cannot only look at it as a hardware problem or challenge or even a single components challenge. The GPUs would not be effective without world-class networking, world-class storage, and world-class CPUs and all of the memory and components. So it's very much a full system solution to do what we do today. And then to make all of that work consistently, reliably, and scalably, you have to have a really well thought out software ecosystem on top of it that lets different developers enter the system at different places. So it's very much an end-to-end stack to truly solve these really, really big AI challenges today.
So all of the elements are interdependent then?
Yes. And, there depends what part of the AI lifecycle you're working on. So training has slightly different requirements than inference will have. They're both complex. There's an overlap of components and software, but the use cases drive different configurations and constraints, let's say. You have to think of these things end to end to be successful.
When I was younger, all I can think of NVIDIA is that once it's on my computer, I have a very powerful computer to play games. So NVIDIA has really, I guess, gone a long way. But let's go back to its capacity to really support new technology, or at least the technology that we have now. And I want to give listeners some basics on the various hardware and infrastructure components that are part of AI systems. Can you outline a few of these?
Yeah, I mean, we kind of touched on them briefly. You can't do this without a full system. The GPU can't operate in isolation. So CPUs are still required. We still need operating system. You still have to have a system running. So you have a CPU, and then you need to have some type of accelerator to do the math acceleration required for training these algorithms or even running inference. It turns out the GPU architecture is almost perfectly aligned with the compute requirements that AI algorithms require. They are inherently parallel. Some would call them embarrassingly parallel. And the larger you can make this compute problem, we've found the more sophisticated these models become. There's a direct correlation between sort of models' abilities and the amount of compute we throw at a problem. So creating large parallel processing accelerators to tackle that component is key. So CPU, GPU. Now you need data, right? Again, in a vacuum, those two things do very little. So you have to have data and you need a lot of it, which means you need storage. And that storage can't just be any storage, depending on how quickly you would like to finish your task, of which these can be significant, months in the beginning to train big LLMs. You need to have a lot of data and you need to be able to get it to the GPUs quickly. So data movement becomes really important. So this involves complex switching technology, complex sort of network adapting technology. All of these nodes that have all these hardware need to be able to talk to each other. And then within the system itself, you often have to spread your problem out over more than one GPU. So you also have to have interconnect technology. So those are sort of the hardware components. There's more details in there, but probably sufficient. I don't know, Brent, if I hit everything. I think I got the core.
Yeah, maybe I could also talk a little bit about what we're internally talking a lot about these days in terms of the different sort of flavors of the compute that May just laid out. So we kind of talk a lot about 3 computer problems these days. So for a lot of problems that are interesting in the geospatial world, you can kind of decompose it into sort of perceive, reason, and acting. And these sort of form a loop. So you would perceive something about the world, you would reason about it, and then perform some action. And that actually maps pretty well to different flavors of the infrastructure components that May was talking about. At NVIDIA, we have something that pairs pretty well with the perceived part, a small, what we call space, weight, and power, or SWAP constrained environments. So compute that would sort of like live next to the sensor. And we would call that our AGX series of computers. Sometimes we just call them Jetsons, but they're essentially like mini little GPUs with CPUs and all the components May was talking about, but just in a lightweight, lower power footprint that can live next to the sensor and pair up with that sensor and perceive the world. Once you've maybe pre-processed the data or performed sort of like your top level analysis at the sensor, a lot of times you need to collect that data or the products and bring those back to, say, a data center where you're going to do more complex reasoning or store it for more complex training later on. And that would be sort of in the data center, right? So you'd downlink the data, you'd get it into a large data center. And so, we have DGX for those types of compute workloads that require a lot more horsepower. So that's probably what people are most envisioning now with all the buzz around like these big AI jobs and thousands of GPUs, right? That would be a big data center run. But that's just kind of like one piece of the puzzle. And then the last one I wanted to point out was leveraging simulation. So more and more these days, we would augment real data that's been collected with hyper-realistic simulation. Sort of like this gap between like real to sim is becoming less and less as simulation technologies mature. We have another set of technology around OVX that would, potentially still live in the data center. It could be a little bit lighter weight compute. It makes use of a different flavor of GPU that has something called RTX or ray tracing. And that's kind of like going back to our heritage as a company with, gaming and really accelerating the visualization for the gaming industry. Turns out that's actually really good for simulation too. So yeah, those kind of three components between edge, data center, and simulation are really important to solving a lot of the problems today.
Right. That's a whole ecosystem. And thank you both for giving that overview. I want listeners to understand how these systems work because when we use something like ChatGPT, we're getting an instant response, but we don't see all that goes on behind the curtain. It's a really complex infrastructure that's allowing us to work with AI, and I think that it's really important to recognize that. Now, many of the people we've interviewed so far have mentioned that geospatial data is a different beast when it comes to AI systems. So, I'm wondering, do the hardware requirements differ when we're using AI to process geospatial data?
So in the hardware space, my inclination would be to say not really. The software space, I would say yes. So what I mean by that is there is nuance to geospatial data where the spatiotemporal aspect of whatever you've collected is key to the insight that you're going to try and derive at the end of whatever processing chain you've woven together. That is where we find gaps today in the developer experience, where the geospatial developer world meets the AI world. So that's where the rough edges come in, is elevating the spatiotemporal aspect of the data as a first-class citizen into the process. There's also implications around scale in memory, right? So these images tend to be quite large, multi-band. Those types of data models don't fit nicely into existing AI frameworks because, frankly, they were designed for different types of imaging data. They were designed for sort of egocentric, terrestrial, human perspective in cameras. And obviously, this has become more sophisticated over time, but there are clear gaps there. But at the bottom of the stack, when you get to the hardware, problem is fundamentally the same. You potentially have more challenges with data movement, data access, and perhaps there's some solutioning in the low-level networking stack to tackle some of that. But by and large, I find the gaps are mostly manifested in software, and the hardware is more or less amenable to the tasks.
Brent, anything to add?
Yeah, I think that one of the interesting things that we've seen is that there's a rich set of existing geospatial algorithms and software that folks make heavy use of. So I'll call out one by name, GDAL, Geospatial Data Abstraction Library. It's a go-to tool for remote sensing data and geoscientists when you're trying to access things like satellite images and different types of remote sensing imagery. in general, that's all been created over the years with a really robust set of CPU-based tools. And so I think some of the architectures that are coming out now that really haven't existed in the past are kind of around a tighter coupling between the CPU and the GPU. So we have like this thing called Grace Hopper now, and it'll be Grace Blackwell in the future, where we have a really interesting high-speed interconnect between the CPU and the GPU. So you want to keep using your, time-tested and proven algorithm that's CPU-based for pre-processing your data, but then you want to make use of your GPU to run the latest AI. Traditionally, there's been sort of this bottleneck between the two that would slow you down, and some of those bottlenecks are getting removed, which should be pretty interesting going forward.
That's something we can definitely look forward to. What are your thoughts on the evolution of NVIDIA's hardware architectures along with the software used in remote sensing? How does AI fit or integrate with traditional remote sensing algorithms?
There's a couple of components that have stood out to me. I just mentioned the Grace Hopper architecture. Hopefully, moving forward here, especially as May was saying, the software tooling starts to mature to support those things. It doesn't have to be AI all the time, right? There's still a lot of great remote sensing algorithms that we've spent as a community a long time developing and understanding, things like atmospheric compensation or sensor calibration that run quite well in the CPU. And as we start to look at how to port some of those to the GPU, we can still make use of the existing CPU codes. So I'm personally excited about being able to make use of that really quick interconnect and kind of look at it as almost one like co-processor.
And May?
I think as in the weeds as the interconnect sounds, it is actually a really key innovation. Because again, the GPU, this accelerator, has all this compute power and it's sitting there. And it's only as effective as the amount of data I can give it at any one time to crunch through. It doesn't matter how many cores I have. If I just give it a little teeny bit of data, it's not going to do anything any faster than maybe a more simple CPU would do, right? So I have to be able to feed data to this device in a way that lines up with how it can really consume it and crunch through those numbers as fast as possible. Because the GPUs have been and are hosted devices by a CPU, the CPU is in control of that data flow to the device you're asking to do all of this work. And so if that interconnect, remained PCIe generations, then we are fundamentally capped. It doesn't matter how fast we make the cores or how fast we make the memory, you will continue to be bottlenecked, limited by how fast I can move data over there. So solving that interconnect problem means I can now consume data that the CPU can go out and grab as quickly as I can read it from memory. It's no longer bottlenecked by PCIe. This means you can train faster. This means you can inference faster. This means you can solve really big problems faster. So it's a very key innovation that the nuance of which I think it's, unless you're in the weeds, can sometimes get missed.
NVIDIA is solving challenges and making advances in many areas of AI. After the break, we dig into what May considers the most important advancement for enabling the AI we have today. I bet you can't guess what it is. Stay tuned to find out.
Want to be at the forefront of geoscience and remote sensing innovation? Then join one of the Geoscience and Remote Sensing Society's technical committees. With 8 committees to choose from, you'll find your niche. From earth science, informatics to data fusion and climate technologies, our committees are driving progress and advancing the state-of-the-art in geoscience remote sensing work. Through our networks, you'll collaborate with global professionals, participate in cutting-edge research, and apply innovations to real-world challenges. Enhance your career, expand your network, and contribute to a better tomorrow. Visit grss-ieee.org and join a technical committee today.
Welcome back. Today we're speaking with Dr. May Casterline, Principal Solutions Architect, and Dr. Brent Bartlett, Senior Solutions Architect, both of whom work at NVIDIA. Before the break, we learned about the different hardware and infrastructure components that go into AI systems. We also learned about some of the challenges currently impacting geoscientists' ability to make the most of these infrastructures, specifically that there are gaps in developer experience for geoscientists. But as May and Brent point out, both hardware and software challenges are quickly being resolved through the new developments by NVIDIA and others. Let's learn more. So I'm curious, in your view, what's been the most important advancement in terms of hardware and infrastructure that's dramatically changed our ability to use AI for geospatial data?
So I think the biggest miracle that's happened is the explosion and democratization of developer interfaces to this technology. So, you used to have to know CUDA. CUDA's low-level programming interface for our GPUs. It's extremely powerful. It's extremely more friendly than it was 10 years ago, but it is still not for the faint of heart. And porting algorithms efficiently into CUDA in and of itself is hard. It's really hard. So the explosion of abstractions and application-focused frameworks and data movement abstract, all of these things have made this incredible hardware accessible to broader and broader developer ecosystems, including geospatial. And that's really what's making all of this possible, is people that don't know anything about, CUDA blocks and threads can have a GPU do this crazy, awesome work for them. And in turn, they create AIs that can do crazy, awesome work for them. So it's this sort of virtuous cycle that really, really kickstarts industries. And geospatial is just one of the, beneficiaries like the rest of us.
Mm-hmm. Yes, that's actually a really great point, May. I mean, the fact that interfaces are so much more user-friendly is a huge change in AI evolution. With this in mind, what challenges with computation hardware and infrastructure still need to be addressed? I'm thinking about scalability here. And maybe this goes with a question, is it important to put the hardware and infrastructure tools into the hands of people?
Well, it depends what you consider hardware and infrastructure tooling, I suppose. I think one of the larger challenges going forward is going to be the scale at which things are being proposed, meaning the problems folks want to solve, the data they want to solve it with, is going to require really large compute infrastructure. And, tens of thousands of GPUs don't just turn on and work by themselves. That is a really complicated, potential failure modes abound problem where you need a very sophisticated stack to manage that. So the big problems come with their own bucket of big problems to solve before you can even get to the work, right? So making these things, these hardware pieces that in and of themselves are, tens of thousands of parts, all work together is challenging. So that's hard. The next one I would say is the bigger we make the problems, the more data hungry they're going to become. Now, remote sensing doesn't typically have that problem. We typically have a pile of data, but there very easily could be a world where we run out of data. And then we have to figure out, how do we solve this problem with the data we have? And then the third, probably biggest looming issue is energy efficiency. These problems aren't getting smaller, like I've just said. So performance per watt that you spend is going to be a really big question that everybody has to ask. So those are in my brain, again, not unique to geospatial, but geospatial gets to come along for this ride with everybody. And those are kind of the big ones I see.
Yeah, energy is definitely important to me and also for a lot of other scientists. Brent, what are your thoughts on this? Do you think we need to curb the demands of data and model development, or are there other potential solutions?
Yeah, so I think there are still a lot of efficiencies to be gained. So one of the things that was eye-opening to me when I started working here is that even for the GPUs that we have out now, over time, they get more efficient. And what I mean by that is that the software that runs on that, the CUDA, the drivers and the CUDA versions, as they progress, are very talented engineers. That this is not me. but dream up new techniques and approaches at a very low, kind of in the weeds, hardware, software, co-design level to create more optimized approaches for that hardware. So as you update your CUDA versions, you'll see this in like MLPerf, the machine learning performance submissions that we make to that independent organization, is that the performance per watt that May was mentioning goes up just as the software gets more mature. That's just one thing that I didn't realize before I got into the weeds and was working here, is that the effort that NVIDIA puts into making the software more optimized over time to make things run faster and use less power. And then one thing I wanted to hit on as an opportunity, especially in the geoscience community, is to consider some interesting energy efficiencies that we could gain for existing approaches that we are running right now. So just as an example, there are a class of physics problems which keep expanding, where it turns out that you can train an AI model to do that equation or do that physics. And okay, why would you do that? So the interesting thing about doing that is that you can leverage a lot of the really efficient inference capabilities. We have a blog up about some of the new AI weather prediction capabilities, and some of the components of that, processing the atmospheric data, they're able to port that into a reliable AI, and that runs 1,000 times faster and uses 3,000 times less energy than a traditional method. And that's just like one example, but those are the types of things that you can achieve if you kind of like open your aperture a little bit and look at how we are doing things now and how you could be doing them with accelerated compute.
So in that aspect, how do we balance efficiency and sustainability in developing and improving the current hardware infrastructure that we have for AI? Is there a breaking point for development of AI hardware?
I mean, not that we've found. We
Fair.
we keep jamming more capability, more magic into these chips. I mean, they are mind-boggling devices that teams thought up and then made real. So I think we will find a way, right? And it's again, I might sound a bit like a broken record, but it is truly this combination of hardware and software, and then sprinkle in, think about the problems differently. I've been talking about this a lot recently, but the best example of this really is our DLSS technology. It's at least a good example of it. This is tech we've encoded or embedded into our gaming products that effectively allows us to leverage an AI approach to deliver high frequency, I don't know the exact number, 120 hertz, 140 hertz, which the high end monitor refresh rate graphics on really high resolutions, 4Ks and 8Ks, I imagine. I'm not a gamer, ironically, working at NVIDIA, so I apologize to the community if I bungled the numbers. But the main point, though, is, there's a demand from that community to have this type of performance, and there is a fundamental hardware limit to what we can do in consumer cards that make them, obtainable by the market. So instead of thinking of how to redo the hardware to solve the ray tracing problem at those refresh rates, we built an AI that does it. So there's an AI that runs an inference that can consume a sort of subsampled ray traced version of the image and infer what the fully ray traced version looks like. So effectively, we've delivered on a high refresh rate, full resolution image without having to solve it in hardware. We've solved it with AI. The only hardware we needed was the AI hardware to run the inference. So it's a completely different technical solution, which in turn shifts your hardware requirements. And I think you'll see a lot of that. It can be hard to give up the math that's worked so well and consistently for years on certain problems. But, when you do hit those walls, like you're alluding to, how are we going to get over this? You have to think differently. And AI is just this wide open field where you can think differently and try it and see what works. And that happened to work quite well.
I love that. We definitely need to start thinking differently about how we apply this technology and how we maximize it. One area that's important to develop too is access. I know AI models require a lot of computing power, especially for geospatial data. But not everyone has access to supercomputers or complex GPU architectures. So, where can they get access to appropriate GPUs?
Sure. Well, there's a couple things. So one is that NVIDIA did recently relaunch our academic grant program. So that's something I encourage folks to check out. And then in terms of GPUs, one of my, I don't know if it's a pet peeve, but one of my sort of insights, especially for compute on like an academic level or like looking at applying algorithms for geoscience, is you don't necessarily need the like H100, A100, or the upcoming B100, like those big like AI data center GPUs. You can actually make a lot of headway using those RTX GPUs. There are gaming versions of those that we've been talking about, but there are also professional visualization versions of those that are maybe a little bit more suited to running, heavy AI jobs. And those are much more available. So, I would encourage folks to check those out as well. I actually use those in my day-to-day job, and they're quite good. So,
yeah, that's really an advantage too to the way we build our compute architecture. So you can build for your workstation and then deploy anywhere, right? So performance will shift depending on what hardware you have underneath it, but you don't have to reprogram it if you've built something on the workstation with an RTX PCIe card and now you're moving into the cloud and you want to run it on their nodes, or maybe you move into an on-prem cluster that has DGXs, for example, that CUDA will run anywhere. The desktops won't solve the big foundational model problems, but they will let folks start getting ahead and making progress to inform, investments or requests to move to the cloud, things like that. So there are a lot of ways to get started doing things that are impactful.
Right. And I think our listeners will be so excited to hear this if they have no idea yet. I mean, a lot of people are just buying these stuff because they're powerful, but not really optimizing the power it has. Okay, this season, I'm exploring this push-pull discussion happening globally about whether AI is going to be more of a help or hindrance in the Earth observation field. Based on the developments we're seeing at NVIDIA and how AI infrastructure is advancing, what are your thoughts?
I think it's obvious we will think it will help. I would hope it's fairly obvious. I mean, I don't see how it can't. It's not going to be void of challenges. There will be new types of challenges to deal with systems that integrate AI. But if you just think of, computer vision is a phenomenal example of exactly how this is helpful, right? So, before CNNs came and really smashed the records and really up-leveled the whole field, people were bending over backwards, building corner detectors and edge detectors and circle finders and band math. We were doing all sorts of backflips to get to how do we tell a computer what something looks like. And then CNN said, just show me examples. Just give me the context and I'll figure it out for myself, right? And it works and it's ubiquitous. And when it first came out, everybody looked at it with squinty, funny eyes, like, is this actually going to solve my problem? And now I think if you went into any business program, government office, and proposed something besides a neural network to solve a computer vision challenge, they would look like you've been under a rock for, 2 decades. So, I have the same optimism for significantly larger problems in geospatial with AI. Specifically with seeing how crazy good LLMs can be. And even if you're looking at them today and saying, well, it's not general purpose AI, or it's not, some superhuman thing that you've envisioned. If you look at the sheer rate, I don't see how you can think we won't solve huge problems that have seemed impossible. It just, it makes you think it's possible, which I think is why I'm very optimistic about it.
I think I'm going to go help. I think anytime we see the sort of general application of deep learning in a particular field, it quickly become state of the art, right? So like May was saying, I can't envision that won't be true with, earth science and remote sensing. I think there are a lot of really compelling examples out there that are starting to show really, really great results. And then to our question on accessibility. So, as is happening right now with large language models, we have big efforts by large entities to make the training possible for the generalized version. But then we have a lot of fine tuning or, grounding that can occur with the generalized model, which requires a lot less compute. I think that will help. The other thing that I am excited about for helping is we really haven't touched on it yet, but it's going to be the topic of code generation. It kind of like folds into the democratization a little bit too, right? So, we in being practitioners of remote sensing or geospatial know a lot of the tools and the APIs and the coding and how to do that. I think we're seeing across the developer community the AI tools that are code generation tools that are fine-tuned for geospatial applications will make creating more new applications a lot easier. And so I think that's a big opportunity for our field, is to sort of democratize that and let more people, maybe even outside of our community, start creating applications that run and allow them to draw their own insights from our data.
AI has been advancing rapidly, and constant innovations, particularly in hardware and infrastructure, help drive this technology further. The design and performance of AI hardware directly influences the way we develop algorithms and transcend limitations. Better and superior hardware allows us to scale AI operations, including in GeoAI. As May and Brent pointed out, the way we design hardware and infrastructure can also help us overcome some of the big downsides to using AI, including power consumption, operational costs, and environmental impact. From what I'm seeing, the constant push to enhance AI also propels advancements in hardware and sustainability. So I think that this synergy between AI and hardware has me thinking that overall, AI will be more of a help than a potential hindrance in the geosciences. In our next episode, we're going to talk about supercomputers, which really puts into perspective the power of hardware and infrastructures like NVIDIA's. In the meantime, learn more about all the exciting work Dr. May Casterline, Dr. Brent Bartlett, and all the other incredible researchers at NVIDIA are cooking up by visiting blogs.nvidia.com. You can also stay up to date on the latest in tech developments at NVIDIA's GTC conferences. Make sure you say hi to May and Brent if you attend. Don't forget to follow and rate us on Spotify and Apple Podcasts, and send some love to our sponsors at IEEE_GRSS on X and Instagram, and IEEE Geoscience and Remote Sensing on Facebook and LinkedIn. This episode was produced by Nicole Bedford from Nicole Bedford Films, with help from me, Stephanie Tumampos. Graphics and design by Mylene Briggs of Kila Media, and a special thanks to Manil Maskey and Fabio Pacifici for their support. I'm Stephanie Tumampos, and you've been listening to Down to Earth.